Black holes are the ultimate cosmic monsters. They represent the most extreme objects permitted by the laws of physics. Regions of space-time where gravity becomes so intense that nothing can escape, not matter, not light, not even information, according to some interpretations. For decades, black holes stood as the theoretical limit of how compressed and powerful an object could become, the endpoint of stellar evolution for the most massive stars. The engines powering quasars at galactic centers, the gravitational wells so deep that space-time itself tears at their boundaries. We thought we understood them. We thought nothing could be more extreme. Then in 2001, a physicist named Pavel Mazur proposed something that should not exist. Working with Emil Motola at Los Alamos National Laboratory, Mazur published a paper that challenged everything astrophysicists believed about the most extreme objects in the universe. They described a theoretical entity that could form where black holes were supposed to exist, but would be fundamentally different, more stable, more powerful, more bizarre in its implications. They called it a gravastar, short for gravitational vacuum star. The name barely hints at how strange these objects might be. Gravastars would look almost identical to black holes from the outside. They would have the same mass, the same gravitational pull at a distance, the same effect on nearby stars and gas. An astronomer observing from far away could not easily distinguish a gravastar from a black hole. Both would appear as dark, massive objects, bending light around them and pulling matter into violent accretion disks. But get closer, probe deeper, and the differences become profound. A black hole has a singularity at its center, where all infalling matter is crushed to infinite density and the laws of physics break down. A gravastar has no singularity. Instead, it has something far stranger, a shell of exotic matter surrounding a bubble of space-time, radically different from anything in our normal experience. The proposal seemed outrageous when first published. Most physicists dismissed it. Black holes were already strange enough, without inventing even weirder alternatives. General relativity predicted black holes clearly. Observations confirmed they existed. Astronomers had identified dozens of stellar mass black holes in binary systems and supermassive black holes at galactic centers. The evidence was overwhelming. Why propose something different? But Mazur and Motola were not crackpots proposing pseudoscience. They were serious physicists working with rigorous mathematics. Their gravastar solution solved real problems that plagued black hole theory, problems that had troubled physicists for decades but which most had learned to ignore or work around. The most severe problem was the information paradox. When matter falls into a black hole, it carries information. The quantum states of every particle, the arrangement of every atom, all the information that defines what the matter is, gets pulled past the event horizon. According to classical general relativity, that information is lost forever, trapped inside the black hole where it cannot affect the outside universe. But quantum mechanics says information cannot be destroyed. It can be scrambled, hidden, transformed, but never truly lost. The total information content of the universe must be conserved. Black holes seem to violate this fundamental principle. Matter goes in, Hawking radiation comes out, but the radiation is random and thermal, containing no trace of what fell in. The information appears to vanish. This paradox had sparked debate for decades. Stephen Hawking initially argued that information really was destroyed, that quantum mechanics needed modification near black holes. Other physicists vehemently disagreed. They proposed that information might be encoded in subtle correlations in the Hawking radiation, or stored at the event horizon, or released in the final burst when the black hole evaporated. None of these solutions was entirely satisfying. The paradox remained an open wound in theoretical physics, a place where our two best theories, general relativity and quantum mechanics, came into direct conflict with no clear resolution. Gravastars offered an elegant solution. If there is no event horizon, If matter never actually crosses a true point of no return, then information need never be lost. Everything that falls toward a gravastar gets encoded in its structure. The information remains accessible in principle, even if retrieving it might be practically impossible. The paradox dissolves. Quantum mechanics and general relativity no longer conflict because the conditions that created the conflict never actually occur in nature. Black holes, with their singularities and information loss, would be theoretical artifacts. Gravastars, strange as they are, would be what really forms when massive stars collapse. The idea gained little traction initially. It was published, noted by specialists, then largely forgotten as the physics community moved on to other problems. But over the past 2 decades, something changed. As observations of black holes became more precise, subtle anomalies emerged. Features in the radiation from accretion disks that did not quite match predictions. Unexpected behaviors during black hole mergers detected by gravitational wave observatories. Nothing definitively wrong, nothing that proved black holes did not exist, but small discrepancies that accumulated and made some researchers wonder. Could these be signs that we were actually observing gravastars instead of black holes? More importantly, theoretical work revealed that gravastars might be more than just alternatives to black holes. They might be stronger. Their exotic matter shells might be able to support higher densities and more intense gravitational fields than anything a conventional black hole could produce. Some calculations suggested gravastars could concentrate energy in ways that made black holes look weak by comparison. The numbers were striking. In certain configurations, a gravastar might generate gravitational forces 100 times more intense than an equivalent mass black hole. 100 times. This was not a minor difference. This was a fundamental shift in what the most extreme objects in the universe could do. If gravastars exist, they would revolutionize astrophysics. They would change our understanding of stellar evolution, galaxy formation, gravitational wave sources, and the ultimate fate of matter. They would solve the information paradox while opening new questions about quantum gravity and the nature of space-time. They would demonstrate that the universe is stranger than we imagined, that the objects we thought we understood are actually something entirely different, and they would show that nature has not yet revealed its most extreme possibilities. That beyond black holes, beyond anything we have directly confirmed, lie entities even more compressed, more powerful, more bizarre. The universe may hide gravastars in plain sight. We have been looking at them for years, calling them black holes, never suspecting that what we observed was something far stranger. Black holes emerge from general relativity with mathematical inevitability. When Albert Einstein published his field equations in 1915, he gave humanity a new understanding of gravity. No longer a force reaching across empty space, as Newton described. Instead, gravity was the curvature of space-time itself. Mass and energy warp the fabric of space and time. Objects follow the straightest possible paths through this warped geometry. What we perceive as gravitational attraction is really objects moving along curves in bent space-time. The equations were beautiful, elegant, and made predictions that matched observations with stunning accuracy. But the equations also predicted something disturbing. Under certain conditions, space-time could become so warped that it would collapse into itself. A region would form where the curvature became infinite, where the geometry ceased to make sense, where all paths led inward and none led out. Within months of Einstein publishing his theory, Carl Schwarzschild found a solution to the field equations describing exactly such a region. A spherical mass compressed to sufficient density would warp space-time so severely that a boundary would form. Inside this boundary, later called the event horizon, escape velocity exceeded the speed of light. Since nothing could travel faster than light, nothing inside could escape. Everything would be pulled toward the center, where it would be crushed to infinite density, at a point called the singularity. Einstein hated this solution. He believed it was a mathematical curiosity with no physical reality. Nature would never permit such extreme conditions to actually occur. Surely some process would intervene before stars collapsed completely. Some pressure would support the stellar remnant and prevent the formation of a singularity. For decades, most physicists agreed black holes were theoretical artifacts, pathologies in the equations that had no counterpart in the real universe. Stars might collapse, but something would stop them before they became black holes. Then J. Robert Oppenheimer and Hartland Snyder published their 1939 paper showing that no known force could prevent sufficiently massive stars from collapsing into black holes. When a massive star exhausted its nuclear fuel, it would collapse catastrophically. The electron degeneracy pressure that supported white dwarfs would be overcome. The neutron degeneracy pressure that supported neutron stars would be exceeded. Nothing in known physics could halt the collapse. The star would shrink past its event horizon and continue collapsing until all its mass concentrated at a singularity. Black hole formation was not just possible, but inevitable for the most massive stars. This should have settled the issue, but it only deepened the problems. The singularity was a place where general relativity broke down completely. Density became infinite. Space-time curvature became infinite. The equations produced nonsensical results, infinities that made calculation impossible. Physicists call these singularities because they represent singular points where the theory fails. General relativity predicts its own breakdown. At the center of every black hole lurks a place where our best theory of gravity cannot tell us what happens. This is not satisfying. A complete physical theory should describe nature everywhere under all conditions. A theory that predicts its own failure is admitting its own incompleteness. Roger Penrose proved in the 1960s that singularities are not artifacts of idealized symmetric solutions. Even without perfect symmetry, even with realistic messy conditions, general relativity still predicts singularity. Formation once collapse begins. This was the singularity theorem, and it earned Penrose the Nobel Prize decades later. The implication was clear. Singularities are generic features of gravitational collapse in general relativity. Any sufficiently massive collapsing object will form a singularity. The theory cannot avoid them. General relativity contains within itself this fatal flaw, this admission that it cannot describe the most extreme gravitational conditions it predicts will occur. Physicists hoped quantum mechanics would rescue the situation. General relativity is a classical theory, meaning it does not incorporate quantum effects. At extreme densities approaching the singularity, quantum effects should become important. Perhaps quantum mechanics would smooth out the singularity, preventing infinite density and maintaining sensible physics all the way to the center. This hope motivated decades of work on quantum gravity, attempting to merge general relativity and quantum mechanics into a unified theory. String theory, loop quantum gravity, and other approaches all promise to eliminate singularities by showing that space-time has quantum structure preventing infinite compression. But quantum gravity remains incomplete. No approach has produced a fully consistent theory making testable predictions. We do not know how quantum effects modify black hole interiors. We can speculate that singularities are avoided but cannot prove it. And even if singularities are avoided, other problems remain. The event horizon itself creates paradoxes. It is a one-way membrane in space-time, a surface of no return. Cross it and you can never come back, never communicate with the outside, never influence anything beyond. This seems to violate quantum mechanics, which demands that physics be reversible, that information not be lost. Stephen Hawking complicated matters further by showing that black holes are not entirely black. Quantum effects near the event horizon cause black holes to emit radiation, now called Hawking radiation. This radiation carries energy away, causing black holes to slowly evaporate. Given enough time, a black hole will radiate away all its mass and disappear. This is where the information paradox becomes acute. If a black hole evaporates completely, what happens to all the information that fell in? The Hawking radiation appears thermal and random, containing no information about what created it. Burn a book, and the information might be preserved in the smoke and ashes in principle. Throw a book into a black hole, and the information seems to vanish when the black hole evaporates. This apparent violation of quantum mechanics has no agreed-upon resolution. These problems are not idle speculation. They are fundamental conflicts between our two best-tested theories. General relativity and quantum mechanics are spectacularly successful in their domains, but black holes bring them into direct confrontation. The singularity shows general relativity failing. The information paradox shows quantum mechanics violated. Something is wrong. Either general relativity requires modification in extreme conditions, or quantum mechanics is incomplete, or both theories need revision. The most straightforward interpretation is that black holes, as general relativity describes them, do not actually exist. They are approximations that break down when examined too closely. Nature does something different, something that avoids singularities and event horizons, something that allows general relativity and quantum mechanics to coexist without contradiction. Gravastars might be exactly that something. Understanding gravastars requires understanding the quantum vacuum. Most people think of vacuum as empty space, nothing there, a void. But quantum mechanics reveals something far stranger. The vacuum is not empty. It seethes with activity. Virtual particles constantly appear in pairs, exist for fleeting moments, then annihilate back into nothingness. This is not speculation or interpretation. The effects of these quantum fluctuations have been measured in laboratories with extraordinary precision. The Casimir effect, the Lamb shift, the anomalous magnetic moment of the electron, all arise from vacuum fluctuations. Empty space is full. These virtual particles carry energy. Not much energy per cubic meter, but the vacuum is vast and the energy adds up. This vacuum energy creates pressure, what physicists call the cosmological constant. Einstein introduced this into his field equations to create a static universe, then abandoned it when cosmic expansion was discovered. But quantum field theory predicts vacuum energy must exist. Every quantum field contributes some over all possible fields and all possible wavelengths, and the total vacuum energy density should be enormous. The calculation gives a number about 10 to the power of 120 times larger than what cosmological observations allow. This mismatch is the worst prediction in physics, off by more than 100 orders of magnitude. Something dramatically wrong is happening with our understanding of vacuum energy. Either quantum field theory grossly overestimates it, or something cancels almost all of it, or our calculation is fundamentally flawed. This is called the cosmological constant problem, and it remains unsolved. But whatever the resolution, quantum mechanics demands that vacuum have energy. That energy has gravitational effects. It curves space-time. Under normal conditions, vacuum energy is negligible compared to ordinary matter and can be ignored. But under extreme conditions, during the Big Bang or inside collapsing stars, vacuum energy might become important. It might affect gravitational collapse in ways general relativity alone does not capture. This is where gravastars enter. Mazur and Motteler proposed that during gravitational collapse, when matter reaches extreme density, quantum vacuum effects become dominant. The collapsing matter does not form a singularity. Instead, it triggers a phase transition in the vacuum itself. The vacuum changes state, transitioning to a configuration with drastically different properties. Think of water freezing into ice. Same molecules, different arrangement, completely different material properties. The vacuum undergoes something similar under extreme pressure. It transitions from its normal state to what physicists call a vacuum condensate, or Bose-Einstein condensate, of gravitational degrees of freedom. This is dense with jargon, but the concept is comprehensible. Under normal conditions, the quantum vacuum has a certain energy density and pressure. Under extreme gravitational compression, it transitions to a different state with different energy density and pressure. The new state has negative pressure. Not just low pressure, negative. It pushes outward rather than pulling inward. This negative pressure can balance gravity, preventing further collapse. The star stops shrinking before it forms an event horizon. The collapse halts at a radius slightly larger than the Schwarzschild radius, the size at which a black hole event horizon would form. The object freezes in this configuration, stable indefinitely. But the structure is bizarre. The interior is not made of ordinary matter compressed to high density. It is made of vacuum in an exotic state, a bubble of space-time with negative energy density, surrounded by a thin shell, where the vacuum transitions from its interior state to its normal exterior state. This shell is where the magic happens. The transition region, just a few Planck lengths thick, perhaps less than 10, to the power of minus 33 centimeters, contains enormous stress energy. The vacuum in the shell is compressed and twisted in ways that generate extreme gravitational effects. This shell supports the entire structure, preventing collapse while generating gravitational fields that can exceed those of black holes. From the outside, the object looks nearly identical to a black hole. It has a surface, not an event horizon, but a physical boundary just above where the event horizon would be. Light can escape from this surface, but barely. Photons climbing out of the deep gravitational well are redshifted to nearly infinite wavelengths. The surface appears dark, nearly black. Matter falling toward the gravastar experiences enormous gravitational acceleration, but crucially, nothing crosses a point of no return. Everything remains in causal contact with the external universe. Information is never lost. The paradoxes that plague black holes do not arise. The stability of gravastars comes from the balance between gravity trying to compress them and the negative pressure of the exotic vacuum state pushing outward. This balance can be remarkably stable. Small perturbations get damped. The structure resists disruption. Unlike black holes, which have no internal structure to support them and collapse to singularities, gravastars have elaborate quantum structure that provides genuine physical support. They are objects in the normal sense, with interiors and surfaces and internal forces, rather than singular points in space-time hidden behind event horizons. The mathematics describing gravastars is complex and subtle. The equations involve general relativity coupled to quantum field theory in curved space-time. Solving them requires careful analysis of how vacuum energy behaves under extreme conditions, how phase transitions occur, how the resulting structure matches smoothly to normal space-time outside. Multiple researchers have worked through these calculations over the past 2 decades. The solutions exist, they are consistent with known physics. They do not violate any established principles. Gravastars are theoretically sound, but do they actually exist in nature? Theory says they are possible, even plausible. Nature might form gravastars instead of black holes when massive stars collapse. The phase transition could occur naturally when matter reaches sufficient density. No fine-tuning or special conditions required, just the behavior of the quantum vacuum under extreme gravitational stress. If this is correct, then most or all of the objects we call black holes are actually gravastars. We have been observing them for decades without recognizing what they truly are. The distinction matters enormously because gravastars behave differently from black holes in subtle ways, ways we might be able to detect, ways that could prove which kind of object we are really seeing when we look at the dark massive entities scattered throughout the universe. The claim seems impossible. How could anything be 100 times stronger than a black hole? Black holes already represent the ultimate gravitational extreme, regions where space-time curves so severely that escape becomes impossible. What could be more extreme than that? The answer lies in understanding what strength means in this context. We are not talking about tensile strength or resistance to being torn apart. We are talking about gravitational field strength, how intensely the object can curve space-time and affect nearby matter and light. In this sense, gravastars can indeed exceed black holes by factors of 100 or more. The key is in the structure. A black hole's mass is concentrated at a singularity hidden behind an event horizon. The gravitational field strength at the event horizon itself is determined by the mass and the horizon radius. For a solar mass black hole, the horizon sits about 3 kilometers from the singularity. The gravitational acceleration at the horizon is enormous but finite. Calculate the tidal forces, the difference in gravity between your head and feet if you fell toward the black hole, and you get specific numbers. These tidal forces increase as you approach the horizon and become infinite at the singularity. But the singularity is hidden. The strongest fields you can actually measure without crossing the point of no return are those at the event horizon. A gravastar has no event horizon and no singularity. Instead, it has a surface, a thin shell, where exotic vacuum matter creates the boundary. This shell can support much higher curvatures than an event horizon can. The reason is that the exotic matter in the shell has negative energy density and negative pressure. These properties allow configurations forbidden for ordinary matter. General relativity relates spacetime curvature to energy and pressure through the Einstein field equations. Normal matter has positive energy and positive or zero pressure. This limits how much curvature normal matter can create, but exotic matter with negative energy can create far more extreme curvature. Think of it this way. Gravity curves spacetime inward toward mass. This curvature is what we perceive as gravitational attraction. Exotic matter with negative energy curves spacetime outward, creating gravitational repulsion. At the gravastar shell, these effects combine in complex ways. The exotic matter pushes outward with enormous negative pressure. This outward push supports a shell that can be incredibly compact and dense. The shell radius can be arbitrarily close to what the Schwarzschild radius would be for that mass. Perhaps just micrometers larger, perhaps less. At this shell, the gravitational field strength reaches values far exceeding those at a black hole event horizon of the same mass. Calculations show this explicitly. Take a star collapsing to form either a black hole or a gravastar. Compare the gravitational field strength at the surface of the gravastar to the field strength at the event horizon of the black hole. The gravastar's surface field can be 10, 50, 100 times stronger, depending on the configuration and how close the shell is to the would-be Schwarzschild radius. The factor varies with the specific model and parameters, but across a range of realistic gravastar models, field strength enhancements of 100 times or more are possible. This is not speculation. This follows directly from solving the Einstein field equations with exotic matter. What does this mean physically? A particle orbiting near the gravastar surface would experience gravitational forces 100 times stronger than the same particle orbiting at the event horizon of a black hole with the same mass. Tidal forces would be 100 times more intense. Light passing close to the gravastar would be deflected 100 times more sharply. The gravitational potential well would be 100 times deeper. In every measurable sense, the gravastar would be 100 times stronger gravitationally than the equivalent black hole. This has profound implications. If gravastars exist, they are the most extreme gravitational environments possible without forming singularities. They concentrate gravity more efficiently than anything else permitted by physics. They can accelerate matter to higher velocities, produce more intense tidal forces, bend light more severely, and warp space-time more extremely than black holes. Yet they avoid the singularities and paradoxes that plague black hole physics. They are stronger and more sensible simultaneously. The enhanced strength comes with observational consequences. Accretion disks around gravastars would be heated to higher temperatures than disks around black holes. The radiation spectrum would be different, peaked at shorter wavelengths, more intense in X-rays and gamma rays. Matter falling onto a gravastar would release more energy than matter falling onto a black hole because it is falling into a deeper potential well. The energy released during gravastar mergers would exceed black hole mergers. The gravitational waves produced would have different characteristics, potentially stronger amplitude and different frequency evolution. None of these differences are enormous. A gravastar does not emit 1,000 times more radiation than a black hole. The spectrum does not shift wildly into new regimes. The gravitational waves do not have completely different form. The differences are subtle, typically 10 to 30% changes in specific observables. But these subtle differences are potentially measurable with current or near-future instruments. If we observe carefully enough, if we compare observations to both black hole and gravastar models, we might see which better matches reality. Some researchers have begun doing exactly this. They take data from X-ray observations of black hole candidates and compare the spectra to both black hole and gravastar predictions. They analyze gravitational wave signals from merging compact objects and check whether the waveforms better match black hole or gravastar models. So far, the results are inconclusive. The data quality is not quite good enough to definitively distinguish the models. Black holes and gravastars both fit current observations within uncertainties. But the analysis shows that future observations could separate them. More sensitive X-ray telescopes, better gravitational wave detectors, more detailed observations of matter near compact objects, all will constrain the possibilities. Within the next decade, we should know whether the objects we call black holes are really gravastars. If even one candidate is confirmed as a gravastar, it will revolutionize astrophysics. We will know that nature avoids singularities through quantum vacuum effects. We will know that the most extreme objects in the universe are even more extreme than we thought, 100 times stronger gravitationally, dense enough and compact enough to challenge the boundaries of what physics allows, strange enough to make black holes seem almost conventional by comparison. The universe would be revealing yet another layer of its complexity, showing us that our models, successful as they are, still miss crucial features of reality at the extremes. If gravastars exist, how can we detect them? They look almost identical to black holes from a distance. Same mass, same gravitational pull, same darkness against the sky. But almost identical is not identical. The differences are small but potentially observable. The key is finding signatures unique to gravastars, features that cannot be explained by black holes, evidence that points unambiguously toward quantum vacuum structure rather than event horizons and singularities. Several such signatures have been proposed. Each tests a different aspect of gravastar physics. Each offers a window into whether the dark, massive objects we observe are what we think they are. The most promising signature involves echoes in gravitational waves. When two black holes merge, they produce a burst of gravitational waves that we can detect with LIGO and Virgo observatories. The waves carry information about the masses and spins of the black holes and the properties of the merger itself. The signal has a characteristic form called a chirp. The frequency increases as the black holes spiral inward, reaching a peak at merger, then ringing down as the final merged black hole settles into its equilibrium state. This entire process typically lasts less than a second. Once the ring down completes, the signal ends. No more waves are emitted except for tiny residual oscillations that decay exponentially. Black holes are expected to produce clean ring downs with no additional features. The merged black hole oscillates briefly, then settles. The gravitational waves reflect this smooth settling process. But gravastars should behave differently. They have surfaces, physical boundaries just above where an event horizon would form. When two gravastars merge, the violent collision produces gravitational waves that travel outward. Some waves escape immediately. Others bounce off the gravastar surfaces, travelling back inward, then reflecting again and travelling back out. These reflected waves create echoes in the gravitational wave signal, repeating patterns that arrive slightly delayed relative to the main signal. The delay depends on the size and structure of the gravastars. For stellar mass objects, the echoes would arrive roughly 10 to 100 milliseconds after the main merger signal. They would be quieter than the main signal, perhaps 10 to 100 times weaker in amplitude. But they would be present, repeating the merger waveform in a distinctive pattern. Black holes produce no such echoes because waves that fall past the event horizon never return. Only gravastars with their physical surfaces can create the reflections necessary for echoes. Finding echoes would be smoking gun evidence that we are observing gravastars, not black holes. Several groups have searched existing gravitational wave data for echoes. Some claim to have found hints, weak repeating patterns in the noise following black hole mergers that might be echoes or might be statistical fluctuation. The signals are at the edge of detectability, not strong enough to confirm conclusively. Other groups analyze the same data and find no evidence for echoes. The debate continues, but even the controversy is progress. It means we can potentially test gravastar physics with data we already have. As gravitational wave detectors improve and more mergers are observed, the search for echoes will become more sensitive. If echoes exist, we will find them. If they are absent, that would suggest gravastars do not exist or have properties different from current models. Another signature involves the final parsec problem in supermassive object mergers. When galaxies collide, their central supermassive black holes eventually sink toward the center of the merged galaxy. Friction with gas and gravitational interactions with stars cause the black holes to spiral inward toward each other. But the final stages, when the black holes are separated by less than a parsec, about 3 light years, should take an extraordinarily long time. The black holes have cleared out stars and gas from their vicinity. Without something to carry away energy and angular momentum, the black holes stall. They can remain separated for billions of years without merging. This is the final parsec problem. We expect black hole mergers should be much rarer than observed because of this stalling. Gravastars might solve this. Their surfaces can interact with each other and with surrounding matter in ways event horizons cannot. During the approach, gravastars could generate tidal distortions, shedding energy through surface waves and gravitational radiation more efficiently than black holes. This would allow them to merge faster, avoiding the final parsec stall. If supermassive mergers occur more frequently than black hole physics predicts, that could be evidence for gravastars. Observations are just beginning to constrain merger rates at these scales. Future gravitational wave observatories operating at lower frequencies will detect supermassive mergers directly. The rate and properties of these mergers will test whether gravastars provide a better explanation than black holes. X-ray observations offer another test. Matter in accretion disks around compact objects gets heated to millions of degrees and emits X-rays. The spectrum of this radiation depends on the temperature, density, and velocity of the accreting matter, which in turn depend on the gravitational field strength near the compact object. Gravastars, with their enhanced surface gravity, would heat accreting matter to higher temperatures than black holes. The X-ray spectrum would be harder, shifted to higher energies, with more emission in the hard X-ray and soft gamma-ray bands. Precise spectroscopy of black hole candidates could reveal whether their spectra better match gravastar or black hole models. Current X-ray observatories like NuSTAR and upcoming missions like Athena and Lynx will provide the spectroscopic precision needed for such tests. Researchers are already comparing observed spectra to gravastar predictions. The results so far are intriguing but not conclusive. Some observations seem slightly better fit by gravastar models. Others match black holes just fine. No single observation definitively proves gravastars exist, but the statistical accumulation of small discrepancies, observations that marginally favor gravastars over black holes, could build a compelling case. Optical and infrared observations might reveal differences in accretion disk structure. The intense gravitational field near a gravastar could affect how the disk forms and evolves. Turbulence and instabilities might differ. The inner edge of the disk, where matter makes its final plunge toward the central object, could behave differently if it encounters a surface rather than an event horizon. Matter hitting a gravastar surface might produce brief flares or oscillations as it settles onto the exotic matter shell. These would create variability patterns distinct from black hole accretion. High-speed photometry of black hole candidates might reveal such signatures. Each of these observational tests probes a different aspect of gravastar physics. None alone will definitively answer whether gravastars exist, but together, multiple lines of evidence pointing in the same direction would be convincing. If gravitational wave echoes are detected, and supermassive mergers occur faster than predicted, and X-ray spectra consistently favor gravastar models, and accretion disk variability shows unexpected patterns, the conclusion becomes unavoidable. The universe makes gravastars, and everything we thought we knew about the most extreme objects in the cosmos needs revision. We would be learning that nature is stranger and more complex than our theories capture, that quantum effects fundamentally alter the endpoints of gravitational collapse, that black holes as we conceive them do not exist, replaced by objects even more extreme and more bizarre. How would a gravastar actually form? This question has troubled theorists since Mazza and Mottola first proposed these objects. Black holes form through well-understood processes. A massive star exhausts its nuclear fuel. Fusion stops. The core no longer produces radiation pressure to counteract gravity. The star collapses catastrophically. If the core mass exceeds about 3 solar masses, neutron degeneracy pressure cannot halt the collapse. Nothing can. The core shrinks through its Schwarzschild radius, forming an event horizon. The collapse continues inside, hidden from view, presumably forming a singularity. The process is violent but straightforward. Gravastar formation must somehow avoid this fate. The collapsing matter must trigger a quantum phase transition before the event horizon forms. The vacuum state must change from its normal configuration to an exotic configuration with negative pressure. This transition must happen at exactly the right moment and in exactly the right way to halt collapse and create a stable structure. The timing is critical. Too early, and the transition fails because pressure and temperature are insufficient. Too late, and the event horizon forms first, trapping everything inside with no chance for a transition to prevent singularity formation. The window seems impossibly narrow. Early critics of gravastar theory focused on this apparent fine-tuning. How could nature reliably produce such precisely timed transitions? The probability seemed vanishingly small. Each stellar collapse would need to thread an incredibly narrow needle to produce a gravastar instead of a black hole. If even 1 in a million collapses succeeded, gravastars would be extremely rare. We would not observe them unless we were extraordinarily lucky. This suggested gravastars, while theoretically possible, were probably not what we actually see in nature. Black holes remained the more plausible explanation for observed compact objects, but more detailed calculations revealed surprising robustness. The vacuum phase transition is not as delicate as initially thought. Under the extreme conditions of stellar collapse, quantum effects become large and unavoidable. Space-time curvature approaches the Planck scale. Energy densities reach values where quantum gravity effects should dominate. In this regime, vacuum phase transitions are not just possible, but may be generic. The vacuum is unstable at such extreme densities. It naturally seeks a lower energy state. That state has negative pressure and can halt collapse. No fine-tuning required, just standard physics in an extreme regime we cannot fully calculate. Think about water freezing. Lower the temperature below 0 Celsius and ice forms. You do not need to carefully tune conditions. The phase transition happens automatically, driven by thermodynamics. Something similar might occur with vacuum under extreme gravitational stress. Compress it enough and it transitions to a different phase. The transition is favoured energetically. It happens reliably. Nature finds this solution naturally without requiring special conditions or unlikely coincidences. If this picture is correct, gravastar formation could be the default outcome of stellar collapse rather than a rare alternative. The transition would proceed in stages. As the stellar core collapses, density and pressure increase. Normal matter is compressed to nuclear densities, then beyond. Nucleons break down into quarks. Quarks themselves might dissolve into more fundamental structures we do not yet understand. At some point, the distinction between matter and vacuum blurs. What we call matter is really excitations of quantum fields. What we call vacuum is the ground state of those fields. Under extreme compression, the ground state changes. The fields reconfigure into a new minimum energy state. This is the vacuum phase transition. It occurs throughout the collapsing core simultaneously once critical conditions are reached. The new vacuum state has radically different properties. Its energy density is lower than the original vacuum, but its pressure is negative. Negative pressure means tension rather than compression. The new vacuum pulls on itself, resisting further compression with exponentially increasing force. The collapse halts, but the transition is not uniform. It proceeds fastest at the center where conditions are most extreme. The outer layers take longer to transition. This creates a shell structure. The inner region rapidly transitions to the new vacuum state. The outer layers continue collapsing inward. They impact the newly formed core, which is now supported by negative pressure. Energy is released in this impact, perhaps explosively, potentially driving off the outer stellar layers. This explosive energy release might be what we observe as supernovae. Conventional supernova theory struggles to explain how the collapse-triggered explosion actually ejects the outer stellar envelope. Computer simulations often fail to produce explosions energetic enough to match observations. The bounce when infalling matter hits neutron degeneracy pressure should create a shock wave, but the shock tends to stall and fail. Neutrino heating or other mechanisms must revive the shock. The physics is complex and uncertain. Perhaps what really happens is gravastar formation. The core transitions to a vacuum condensate state. Infalling matter strikes this exotic core and rebounds violently. The energy released is more than sufficient to explode the star. Supernova would be the birth announcements of gravastars. After the explosion, the gravastar settles into equilibrium. The vacuum condensate core is surrounded by a thin shell of transitioning vacuum, perhaps just a few Planck lengths thick. Outside this shell, spacetime is normal. The structure is stable. Small perturbations damp out. The gravastar can exist indefinitely without further evolution. It is not a transient state or an unstable configuration. It is an endpoint of gravitational collapse, just as valid as a black hole, but without the pathologies. This stability is crucial. If gravastars were unstable, they would not last long enough for us to observe them. But if they are stable, they could constitute most or all of the compact objects we see. Accretion onto a gravastar would not fundamentally alter it. Matter falling toward the surface encounters enormous gravitational forces, but it never crosses an event horizon because there is not one. Instead, it hits the gravastar surface at relativistic speeds. The kinetic energy is converted to radiation and heat. The exotic matter shell absorbs some energy and mass but remains thin and stable. The gravastar mass increases gradually as it accretes. Its radius adjusts slightly to maintain equilibrium. The process is more like matter accumulating on a planet than matter disappearing into a black hole. Information is never lost. Everything remains in causal contact with the external universe. Mergers between gravastars would be extraordinarily violent. Two objects with surfaces and internal structure colliding at relativistic speeds. The exotic matter shells would distort and possibly rupture during the collision. Enormous energies would be released as gravitational waves and electromagnetic radiation. The structures would merge, their vacuum condensate cores combining, their shells reconnecting to form a single, larger gravastar. The process would be messy and complex, nothing like the clean, geometric merger of black holes, which are essentially structureless except for mass and spin. Gravastar mergers should have distinctive signatures in both gravitational waves and electromagnetic counterparts. If this formation picture is correct, the universe has been making gravastars all along. Every supernova that would conventionally produce a black hole actually produces a gravastar instead. The objects we call stellar mass black holes are gravastars. The supermassive objects at galactic centers are gravastars, grown large through accretion and mergers over billions of years. We have been observing gravastars for decades without recognizing them because they look almost identical to black holes from outside. The differences only become apparent in detailed observations sensitive to the quantum structure hidden just beneath what we thought was an event horizon. Nature chose a more complex solution to gravitational collapse, one that avoids singularities and information loss by leveraging quantum properties of the vacuum, and we are only now beginning to suspect this might be true. Gravastars could be the most powerful energy sources in the universe. More powerful than supernovae, more powerful than gamma-ray bursts, more powerful even than black hole mergers. The reason lies in that exotic matter shell with its negative energy density and enormous stress energy. Under the right conditions, this shell could release energy in ways that dwarf any other astrophysical process. This is not idle speculation. The calculations are done. The physics is understood. If gravastars exist, and if they can be triggered into certain instabilities, the energy release would be catastrophic on a cosmic scale. The key is in the shell structure. The thin layer of transitioning vacuum contains more energy density than anything else in nature, except possibly the early universe during inflation. This energy is normally locked into the vacuum structure itself, stabilizing the gravastar. But perturbations could potentially destabilize it. A sufficiently violent impact, extreme tidal forces during a near collision, or accumulation of accreted matter pushing the gravastar past some critical threshold. Any of these could trigger a transition. The vacuum shell could reconfigure, releasing its enormous stored energy in a burst lasting perhaps milliseconds. How much energy? The calculations are striking. A solar mass gravastar shell might contain energy equivalent to a significant fraction of the entire rest mass energy of the Sun. That is 10 to the power of 47 joules. For comparison, a supernova releases about 10 to the power of 44 joules. The shell contains 1,000 times more energy. If even 1% of the shell energy could be liberated suddenly, the explosion would outshine a supernova by a factor of 10. If 10% could be released, the event would be 100 times more luminous than any supernova ever observed. Such explosions might already have been seen. Gamma-ray bursts are the brightest electromagnetic events known. Brief flashes of gamma rays that can outshine entire galaxies for seconds to minutes. The most powerful gamma-ray bursts release energies comparable to supernovae, but concentrated in gamma rays rather than visible light. We observe hundreds of gamma-ray bursts per year, coming from random directions across the sky. The Standard Model attributes long-duration bursts to collapsing massive stars and short-duration bursts to neutron star mergers. But the energy production mechanism is not entirely understood. How do these events convert gravitational energy into gamma rays so efficiently? Gravastar shell instabilities offer an alternative explanation. A gravastar, pushed past stability, could undergo a vacuum phase transition in reverse. The exotic vacuum state in the shell transitions back to normal vacuum. This releases the energy difference between the two vacuum states as a burst of high-energy particles and gamma rays. The energy is released from the entire shell simultaneously, creating a spherical explosion. If the gravastar is rotating, the explosion might be beamed into jets by magnetic fields, focusing the energy into narrow cones. This could naturally explain the beaming observed in many gamma-ray bursts. The explosion would also produce gravitational waves, the violent reconfiguration of the gravastar structure as the shell transitions would shake space-time powerfully. These gravitational waves would have different characteristics than waves from black hole or neutron star mergers. They would be broader band, covering a wider range of frequencies. They would have distinctive polarization. They would arrive simultaneously with the gamma-ray burst rather than minutes or hours before or after, as in standard merger scenarios. Detecting gravitational waves coincident with gamma-ray bursts and showing gravastar-specific features would be strong evidence that gravastars exist and can undergo explosive transitions. Even without complete shell destabilization, gravastars could generate enormous power through accretion. Matter falling onto the gravastar surface releases gravitational potential energy. Because the gravitational field near a gravastar surface can be 100 times stronger than near a black hole event horizon, the energy release per unit mass is correspondingly higher. An accretion rate of 1 solar mass per year onto a gravastar could generate luminosity exceeding the Eddington limit by large factors. The Eddington limit is normally the maximum luminosity an object can have before radiation pressure exceeds gravitational attraction and blows away the accreting matter. But gravastars, with their intense surface gravity, could potentially exceed this limit substantially. This has implications for active galactic nuclei and quasars. These are powered by supermassive compact objects at galactic centers accreting matter from surrounding gas and stars. The luminosity can reach 10 to the power of 40 watts, outshining the entire galaxy. Black hole models explain this by having matter spiral inward through an accretion disk, gradually releasing energy as it descends into the potential well. But some quasars appear too luminous for their measured black hole masses. They seem to violate the Eddington limit. If the central objects are gravastars instead of black holes, the apparent violation goes away. The enhanced gravitational field allows higher accretion rates and more efficient energy conversion. Gravastar shells might also generate energy through quantum processes. The extreme curvature and exotic matter could create particle production through Hawking-like mechanisms. Virtual particles in the intense fields could be pulled into real particles, extracting energy from the gravitational field. These particles would be emitted as radiation, creating a steady luminosity even without accretion. The spectrum would differ from Hawking radiation from black holes. It would be hotter, more intense in high-energy photons. Observations of isolated compact objects not actively accreting might reveal this signature radiation if gravastars exist. Another intriguing possibility involves vacuum energy extraction. The gravastar shell exists in a lower energy vacuum state than the surrounding space. This energy difference is what provides the negative pressure supporting the structure. But energy differences can be tapped. Advanced civilizations far in the future might learn to manipulate gravastar shells, extracting vacuum energy directly. This would be the ultimate power source, not fusion of matter, not annihilation of matter and antimatter, but direct conversion of vacuum structure into usable energy. The physics allows it in principle, though the engineering would be beyond anything we can currently imagine. If this seems like science fiction, remember that all technology is based on physics. We harness electromagnetic energy through generators and solar panels because we understand electromagnetism. We release nuclear energy through fission and fusion because we understand the strong force. If we truly understand vacuum energy and gravastar structure, technologies might emerge that seem miraculous by current standards. Extracting energy from the quantum vacuum would provide power without fuel, without waste, limited only by how fast you can draw energy from the vacuum state. A single gravastar could power a galactic civilization for billions of years. Even if we never achieve such technologies ourselves, other civilizations might. If life is common in the universe, some species should reach technological maturity millions or billions of years before us. They would have time to develop vacuum energy technology. They might construct artificial gravastars, optimized for energy extraction. We might observe their megastructures as anomalous compact objects, with properties not matching natural gravastars or black holes. Searching for such signatures would be a new form of SETI, looking not for radio signals, but for evidence of vacuum engineering. The universe might contain artifacts we have mistaken for natural objects. Whether natural or artificial, gravastars represent power on a cosmic scale. Their exotic structure embodies energies far exceeding anything achievable with normal matter. They could produce the brightest explosions in the universe. They could power the most luminous quasars. They could provide energy to civilizations spanning galaxies, all from the quantum properties of empty space twisted into exotic configurations by extreme gravity. If gravastars exist, they are not just curiosities of theoretical physics. They are the ultimate power sources, 100 times stronger than black holes, and possibly the key to understanding the most energetic phenomena the universe displays. We have been seeing their effects for decades. We just did not recognize what we were observing. Black holes create paradoxes that have troubled physicists for half a century. The information paradox is most famous, but not the only problem. There is also the firewall paradox, the complementarity paradox, issues with unitarity, quantum entanglement apparently violated across event horizons, and the fundamental conflict between general relativity, predicting singularities, and quantum mechanics forbidding them. These are not minor technical issues. They represent deep contradictions between our two best-tested theories. Gravastars elegantly resolve all of them simply by avoiding event horizons and singularities entirely. If gravastars exist, the paradoxes never arise because the conditions that create them never occur in nature. Start with the information paradox. When matter falls into a black hole, it carries quantum information, the specific quantum state of every particle, all the correlations and entanglements, everything that defines what the matter is physically. Classical general relativity says this information crosses the event horizon and becomes trapped inside. It cannot affect the exterior universe anymore. The black hole is characterized completely by its mass, charge, and angular momentum. All other information is hidden. This is the no-hair theorem. Black holes have no hair, no additional features distinguishing one from another beyond these three numbers. But Stephen Hawking showed that black holes evaporate through quantum effects near the event horizon. Virtual particle pairs form. One particle falls in, the other escapes as Hawking radiation. The black hole slowly loses mass. Given enough time, it evaporates completely. The problem is that Hawking radiation appears to be completely thermal. It contains no information about what fell into the black hole. Burn a book, and in principle, you can reconstruct it from the smoke and ashes. Throw a book into a black hole, and the information seems to vanish when the hole evaporates. Quantum mechanics says information cannot be destroyed. General relativity says it is. Contradiction. Decades of work have proposed solutions. Maybe information is encoded in subtle correlations in the Hawking radiation. Maybe it is stored at the event horizon as a hologram. Maybe it escapes in the final burst when the black hole evaporates completely. Maybe the information does not fall past the horizon, after all, but is somehow reflected back. Each proposal has problems. None completely satisfies everyone. The paradox persists as an open wound in fundamental physics. It tells us something is wrong with our understanding of black holes or quantum mechanics, or both. Gravastars eliminate the paradox entirely. There is no event horizon. Information never crosses a point of no return. Everything remains in causal contact with the external universe, always. When matter falls toward a gravastar, it hits the surface. The information in that matter gets encoded in the gravastar structure. The exotic vacuum shell adjusts to accommodate the additional mass and information. Nothing is lost, nothing is hidden behind a horizon. The gravastar can in principle release that information later through radiation or other processes. Quantum mechanics is satisfied, information is conserved, the paradox disappears because the conditions required to create it never occur. The firewall paradox suffers a similar fate. This paradox arises from carefully analysing quantum entanglement near black hole event horizons. Hawking radiation particles must be entangled with particles inside the black hole to carry information out, as some solutions to the information paradox require. But those internal particles are also entangled with earlier Hawking radiation, already far from the black hole. A quantum state cannot be maximally entangled with two different systems simultaneously. Something must break. The proposed solution is that a firewall of high-energy particles forms at the event horizon, destroying any information or observer that tries to cross. But this violates the equivalence principle, the idea that freely falling observers see nothing special at the horizon. Black holes with firewalls would be dramatically different from what general relativity predicts. Gravastars have no horizon, so the firewall paradox never arises. Entanglement issues at a horizon are avoided because there is no horizon. Particles approaching the gravastar surface interact with that surface. They do not cross into a separate interior region. The entanglement structure is straightforward. No paradox, no firewall, no violation of equivalence principle because there is no special surface where physics changes discontinuously. Everything is smooth and unparadoxical. Singularities present another problem gravastars resolve. General relativity predicts that collapsing matter forms singularities where density and curvature become infinite. But infinities in physics usually indicate theory breakdown. They suggest we are asking questions beyond the theory's valid domain. Quantum mechanics should modify physics at very small scales and very high energies. But we do not have a complete theory of quantum gravity, telling us how singularities are avoided. We hope singularities are replaced by some kind of quantum structure. But we do not know what that structure is. Black holes contain singularities we cannot describe properly. This is unsatisfying. Gravastars avoid singularities naturally. The vacuum phase transition prevents collapse from reaching infinite density. The quantum vacuum structure provides physical support stopping the collapse before singular conditions arise. No infinities appear. The gravastar interior is unusual, exotic, operating in regimes where quantum gravity effects are important, but it is describable with known physics. No singularities, no breakdown of the theory. This is a major advantage. Gravastars give us objects that behave like black holes, observationally, but without the theoretical pathologies. Unitarity is another issue gravastars address. Quantum mechanics requires that probabilities sum to 1, and that time evolution is reversible. If you know the quantum state now, you can calculate it at any past or future time uniquely. This is unitarity. Black holes seem to violate it. Information falls in but does not come out, at least not in a way that preserves the unitary evolution. This suggests quantum mechanics needs modification in the presence of strong gravity. But modifying quantum mechanics is dangerous. It works so well in every other context. Why should black holes be different? Gravastars preserve unitarity because they preserve information. The evolution is reversible in principle, even if chaotic and practically irreversible. This is the same situation as in ordinary thermodynamics. Scrambling an egg is in principle reversible, but practically impossible to undo. Gravastars scramble information that falls onto them. The information is encoded in incredibly complex ways in the quantum structure of the exotic vacuum shell. Retrieving it would require reversing a vast number of quantum processes, practically impossible, but not fundamentally forbidden. Unitarity is preserved. Quantum mechanics requires no modification. Complementarity is resolved similarly. This is the idea proposed by Leonard Susskind, that observers far from a black hole and observers falling into it see complementary but different descriptions of reality. An exterior observer sees information never cross the horizon and eventually get returned in Hawking radiation. An infalling observer sees nothing special at the horizon and falls smoothly toward the singularity. Both descriptions are somehow true simultaneously. Complementary aspects of reality, like wave-particle duality. But the idea is controversial and seems to violate basic causality. Two observers should agree on what happens. With gravastars, there is no complementarity problem. All observers agree on what happens. Matter falls onto the gravastar surface. Information gets encoded there. The surface exists in the normal causal structure of space-time. There is no interior region disconnected from the exterior. No need for complementary descriptions. Everyone sees the same physics from different perspectives as normal. The issue that complementarity was invented to address simply does not arise. All these paradoxes stem from event horizons and singularities. Remove those features and the paradoxes vanish. This is not cheating or avoiding the problem. This is recognizing that the paradoxes might be telling us black holes as classically conceived do not exist in nature. They are good approximations in many contexts. The mathematics of event horizons and Schwarzschild geometry is elegant and useful, but the ultimate endpoint of gravitational collapse might be something slightly different, something that looks almost identical from outside but has fundamentally different structure underneath. Gravastars provide exactly this. They resolve the paradoxes not by finding clever workarounds within black hole physics, but by showing black hole physics is incomplete. Nature found a better solution, one that satisfies both general relativity and quantum mechanics, without forcing them into conflict. We just had not recognized it until we looked carefully at what quantum vacuum effects might do under extreme conditions. The search for evidence of gravastars has intensified dramatically in recent years. Initially, a niche topic discussed by a handful of theorists, gravastar physics has now entered the mainstream of astrophysics. Multiple observational programs are actively looking for gravastar signatures. Some focus on gravitational waves, others analyze X-ray spectra. Still others study the dynamics of stars orbiting the supermassive compact object at our galaxy's center. Each approach tests different predictions of gravastar models. None has yet provided definitive proof, but intriguing hints have emerged. The next decade will likely settle whether gravastars exist. The most exciting hunt involves gravitational wave echoes. We discussed earlier how gravastar mergers should produce echoes, repeated patterns in the gravitational wave signal caused by waves bouncing off the gravastar surfaces. Several research groups have developed sophisticated analysis techniques to search for these echoes in LIGO and Virgo data. The challenges are formidable. The echoes are much quieter than the main merger signal. They arrive when detector noise is increasing as the signal fades. Distinguishing genuine echoes from statistical fluctuations requires careful statistical analysis. In 2016, Jahed Abedi and collaborators published results claiming detection of echoes in the gravitational wave data from several black hole mergers observed by LIGO. The echoes appeared at the expected times and frequencies if the merging objects were gravastars rather than black holes. The statistical significance was moderate, around 3 sigma, meaning roughly 1 in 1,000 chance the signal was random noise. Not strong enough to claim discovery, but intriguing enough to warrant further investigation. The paper sparked intense debate. Other groups reanalyzed the data using different methods. Some confirmed weak evidence for echoes, others found no significant signal. The controversy continues. Multiple papers have been published, arguing both sides. The issue is that extracting such weak signals from noisy data is inherently difficult. Different analysis choices, different statistical techniques, different assumptions about noise properties all affect the results. What one group considers a detection, another considers consistent with noise. This is frustrating, but normal in cutting-edge science. The way forward is more data. As LIGO and Virgo continue operating and detecting more mergers, the echo searches will become more sensitive. If echoes are real, they will show up in multiple events with consistent properties. If they are noise, they will not repeat reliably. Upcoming gravitational wave detectors will help enormously. LIGO and Virgo are being upgraded to improved sensitivity. The Kagra detector in Japan is coming online. The LIGO India detector is under construction. Each additional detector in the network improves our ability to distinguish signal from noise. More importantly, the next generation detectors, like the Einstein telescope in Europe and Cosmic Explorer in the United States, will have sensitivity 10 times better than current detectors. They will see mergers much more clearly. Echoes, if they exist, will be obvious in the data. Within 15 years, these detectors should definitively answer whether gravastar echoes occur. X-ray observations provide another avenue. Multiple satellites are currently monitoring black hole candidates in X-ray binary systems. These are stellar mass compact objects, accreting matter from companion stars. The accreted matter forms a hot disk emitting X-rays. The spectrum depends on the temperature and density structure of the disk, which in turn depends on the gravitational field near the compact object. Gravastar models predict subtly different spectra than black hole models, shifted slightly to higher energies because of the stronger gravitational field near the gravastar surface. Several groups have fit both black hole and gravastar models to observed X-ray spectra. The results are mixed. Some sources seem better fit by gravastars, Others match black holes equally well within uncertainties. No source definitively requires a gravastar. But the statistical trends are interesting. When many sources are analysed together, there is a weak preference for gravastar models. Not strong enough to be convincing yet, but suggestive. More data from current missions like NewStar and future missions like Athena and Lynx will clarify the situation. If gravastars exist, the improved spectral resolution should make their signatures unmistakable. The Event Horizon Telescope provides yet another test. This global network of radio telescopes acts as a planet-sized dish, achieving resolution sufficient to image the event horizon of the supermassive black hole at our galaxy's center and the black hole in the galaxy M87. The famous images released in 2019 showed a dark shadow surrounded by a bright ring. The shadow size and shape matched black hole predictions beautifully. But could they also match gravastar predictions? Yes, at least approximately. Gravastars would also cast shadows because photons passing too close would be captured by the intense gravitational field. The shadow size and shape depend primarily on mass and spin, both the same for gravastars, and black holes of equal mass. The differences are subtle, perhaps a few % variation in shadow shape or brightness distribution. Current images do not have sufficient resolution to distinguish these subtle differences. But the Event Horizon Telescope continues to improve. More telescopes are joining the network. Observations at multiple wavelengths provide additional constraints. Future images will reveal finer structure around the shadow. If gravastars exist, we should eventually see deviations from pure black hole predictions in these ultra-high-resolution images. Another approach studies the dynamics of stars orbiting close to the galactic center supermassive object. Several stars have been tracked for decades, their orbits precisely measured. One star, S2, has an orbital period of 16 years and passes within about 120 astronomical units of the central object. Monitoring S2's orbit tests general relativity in strong gravitational fields. The orbit shows the expected relativistic precession predicted by general relativity for a black hole. But would a gravastar produce the same precession? Almost, but not exactly. The differences are tiny at the limits of current measurement precision, but precision keeps improving. The gravity instrument on the Very Large Telescope in Chile can track stellar positions to within tens of microarc seconds. Over multiple orbits of S2 and other close stars, subtle deviations from black hole predictions might accumulate to detectable levels. If the central object is a gravastar, its slightly different mass distribution and stronger near-surface gravity might cause orbital perturbations distinguishable from a black hole. The observations are ongoing. Every time S2 passes close to the center, we test whether its orbit matches black hole or gravastar models better. Beyond these specific programs, a general strategy is emerging. Look for anomalies in observations of compact objects. Any feature that does not quite match black hole predictions could be a gravastar signature. Unexpected spectral features, unusual variability, surprising merger rates, orbital dynamics that seem slightly off. Each anomaly might have conventional explanations, but if many anomalies appear and all point in the direction of gravastars, the cumulative case becomes compelling. This is how science often works. Not one dramatic discovery, but accumulation of evidence from many directions, all suggesting the same conclusion. Within the next decade, the observational campaign should reach critical mass. Gravitational wave detectors will have observed hundreds of mergers. X-ray observatories will have spectra of dozens of compact objects at high resolution. The Event Horizon Telescope will have multi-wavelength images of multiple supermassive objects. Stellar dynamics measurements will have tracked multiple orbits with exquisite precision. If gravastars exist, this flood of data will reveal them. The signatures will emerge from noise and become statistically robust. Conversely, if gravastars do not exist, the predictions will fail to match observations, and the hypothesis will be ruled out. Either outcome advances our understanding. We will know whether the universe makes gravastars, or whether black holes truly are the endpoint of gravitational collapse. The answer is coming. We just need to keep observing and analysing carefully. The universe will tell us what it contains if we listen closely enough. If gravastars are confirmed to exist, the implications for fundamental physics would be profound and far-reaching. This would not be a minor correction to astrophysics or a curious detail about exotic objects. This would be evidence that quantum effects dominate in regimes we currently cannot calculate, that vacuum structure is far richer than standard quantum field theory captures, and that nature avoids singularities through mechanisms we are only beginning to understand. It would point the way toward quantum gravity, the long-sought theory unifying general relativity and quantum mechanics, and it would raise new questions more challenging than those it answers. First, gravastars would prove that quantum phase transitions of the vacuum occur under extreme conditions. We know phase transitions happen for ordinary matter. Water freezes to ice, iron becomes magnetic below the Curie temperature, liquid helium becomes superfluid below the lambda point. These transitions involve changes in the organization of matter at the molecular or atomic level, while the fundamental laws remain unchanged. Vacuum phase transitions are more radical. The vacuum itself, the ground state of quantum fields, changes its structure. The effective laws of physics, how particles interact, and what forces exist could differ in different vacuum states. We have theoretical evidence for vacuum phase transitions in the early universe. Cosmologists believe the universe underwent several such transitions as it cooled after the Big Bang. The electroweak phase transition separated electromagnetic and weak forces. The QCD phase transition confined quarks into protons and neutrons. These transitions shaped the universe we observe. But they occurred at temperatures and densities we can barely reproduce in particle accelerators. We cannot study them directly. Gravastars would provide natural laboratories where vacuum transitions occur continuously as matter collapses. By observing gravastars, we would learn about vacuum physics in regimes unreachable by any experiment. This connects to one of the deepest problems in physics, the cosmological constant problem. Quantum field theory predicts the vacuum has enormous energy density, 10 to the power of 120 times larger than observed. Something must cancel almost all of this vacuum energy, leaving only the tiny amount we attribute to dark energy. We have no idea what mechanism does this cancelling or why it is so precise. Gravastar physics might provide clues. If vacuum can transition between states with vastly different energy densities, perhaps the cancellation is dynamical. Perhaps vacuum adjusts itself to minimize total energy under given conditions. Perhaps the nearly zero cosmological constant we observe is an equilibrium value reached through processes related to what happens in gravastar formation. Gravastars would also inform quantum gravity research. String theory, loop quantum gravity, and other approaches all attempt to describe space-time at the Planck scale, where quantum effects should dominate. None have produced testable predictions in accessible regimes, but all predict that singularities are avoided and that quantum effects smooth out space-time at small scales. Gravastars would provide observational evidence that nature indeed avoids singularities through quantum mechanisms. This would vindicate the basic premise of quantum gravity research while constraining what mechanisms are at work. Different quantum gravity theories make different predictions about how singularities are avoided. Gravastar observations could discriminate between approaches, telling us which theories are on the right track. The exotic matter in gravastar shells has properties that challenge our understanding. Negative energy density and negative pressure are permitted by quantum field theory, but are usually confined to tiny quantum fluctuations. Macroscopic amounts of exotic matter with these properties seem impossible to create under normal conditions. The Casimir effect produces negative energy, but only in microscopic gaps between conducting plates. Hawking radiation involves negative energy particles falling into black holes, but in infinitesimal amounts. Gravastars would demonstrate that exotic matter can exist in bulk, in quantities measured in solar masses, stabilized into structures that persist for billions of years. How is this possible? What quantum states of matter or vacuum can have these properties at macroscopic scales? Answering these questions would require new physics beyond the standard model of particle physics. New fields, new interactions, new particles perhaps. Or maybe deeper understanding of known fields under extreme conditions we have never analysed properly. Either way, gravastar physics would point toward extensions of current theory. This is exciting. The standard model is spectacularly successful, but clearly incomplete. It does not include gravity. It does not explain dark matter or dark energy. It has parameters that seem arbitrary and finely tuned. Discovering new physics through gravastar observations would provide clues about how to extend the standard model. What new ingredients are needed? What principles determine the parameters? Gravastars might also connect to other mysteries. Could a dark matter be related to vacuum structure? Perhaps dark matter particles are excitations of exotic vacuum states, related to the vacuum that forms gravastar interiors. This is speculative but not impossible. Dark matter has never been detected despite decades of searching. Maybe we have been looking for the wrong things. Maybe dark matter is not a new particle species, but a property of vacuum in certain states. Gravastar physics might reveal these connections. There are philosophical implications as well. Gravastars show that nature is more subtle than our equations capture. General relativity predicts black holes with singularities. Quantum mechanics suggests singularities should be avoided. Nature apparently agrees with quantum mechanics and implements a solution we had not fully anticipated. Continue. 7:58 p.m. This humility is important. Our best theories are approximations, valid in certain regimes, but incomplete. We must remain open to surprises, to nature implementing solutions we have not yet imagined. Gravastars would be exactly such a surprise. Predicted by nobody before careful analysis of exotic physics, unexpected by the community, initially dismissed as unlikely, yet potentially real and ubiquitous. Finally, gravastars would change how we think about the future of the universe. Black holes are often described as eternal objects that will outlast everything else. In the far future, trillions of years from now, after stars have died and galaxies dispersed, black holes will remain. They will slowly evaporate through Hawking radiation, but will persist for time so long they are effectively eternal. But if gravastars replace black holes, the story changes. Gravastars are stable, but not necessarily eternal. Their exotic vacuum states might slowly decay over cosmological timescales, or they might be disrupted by rare quantum fluctuations. The very far future might not be dominated by black holes evaporating into nothing, but by gravastars transforming into new structures we cannot yet predict. The ultimate fate of matter and energy in the universe might be richer and stranger than we thought. All of this flows from the simple realization that extreme gravity might trigger vacuum phase transitions. One idea with implications cascading through cosmology, astrophysics, particle physics, quantum gravity, and philosophy. This is why gravastars matter. Not just as alternatives to black holes, not just as curiosities, but as windows into physics we cannot access any other way. If they exist, and if we can confirm their existence through observation, we will have discovered a new frontier, a regime where quantum mechanics and gravity merge in ways we are only beginning to understand, where vacuum becomes exotic matter and space-time develops structure beyond what our current equations describe. The universe would be revealing its deeper layers, showing us that the most extreme objects are not the end of the story, but the beginning of a new one. We thought we had found the ultimate limit. Black holes seem to represent the absolute extreme of what gravity could accomplish. Dense beyond imagination, powerful beyond measure, strange beyond comprehension. Objects where space-time warps so severely that the mathematics breaks down and physics admits defeat. We accepted this. We built careers studying black holes. We designed experiments to detect them. We celebrated when gravitational waves confirmed they merged exactly as predicted. The universe seemed to match our theories beautifully, but perhaps too beautifully, perhaps too simply. Nature rarely does simple. Every time we think we have reached the bottom, a new layer reveals itself. Atoms were indivisible until we discovered electrons and nuclei. Nuclei were fundamental until we found protons and neutrons. Protons and neutrons were particles until we discovered quarks. Each layer seemed like the end until someone looked closer and found structure underneath. Why should black holes be different? Why should they be the only objects in the universe with no internal structure, no deeper layer, nothing beneath the surface except singularities and paradoxes? Gravastars suggest black holes are not the end, they are approximations. Good approximations for most purposes, the mathematics of event horizons and Schwarzschild geometry works well enough for many applications. But underneath, something more complex is happening. Quantum vacuum effects that we cannot fully calculate create structure where we thought there was none. Exotic matter that challenges our understanding stabilizes configurations we thought impossible. The universe implements solutions we had not considered because they seemed too bizarre, too unlikely, too difficult to achieve. But nature is not constrained by what we think is likely or simple. It does what the laws of physics permit, and the laws apparently permit gravastars. If gravastars exist, we have been wrong about black holes for half a century. Not completely wrong. The predictions for gravitational fields at large distances are correct. The gravitational wave signals from mergers are nearly right. The appearance of black hole shadows is approximately accurate. But the core assumptions, that event horizons exist and singularities form, are wrong. We have been studying shadows and calling them the objects. We have been analysing approximations and treating them as exact truths. The universe has been showing us something slightly different all along, and we missed it because we were not looking for the right signatures. This is not embarrassing. This is how science progresses. We build models that explain observations. We test those models. When discrepancies emerge, we refine the models or develop new ones. Black holes explained so much and worked so well that we had no reason to question them seriously until recently. But now, observations are becoming precise enough to test the details. Gravitational wave echoes, if they exist, were undetectable until LIGO achieved its extraordinary sensitivity. X-ray spectroscopy, distinguishing black hole from gravastar models, requires resolution that previous satellites could not achieve. We are entering an era where our instruments finally match the precision needed to test these ideas, and the universe might be about to surprise us. The surprise would be profound. Gravastars, 100 times stronger than black holes. Exotic matter with negative energy density forming stable structures. Vacuum phase transitions halting gravitational collapse. Quantum effects dominating in regimes where general relativity predicts classical behavior should prevail. Information preserved instead of lost. Singularities avoided instead of formed. Paradoxes resolved instead of accepted as fundamental mysteries. Every aspect of black hole physics would need reconsideration. Textbooks would need rewriting. Courses would need updating. Researchers would need to learn new physics and abandon comfortable assumptions. But this is exciting, not threatening. We entered science to discover how nature works, not to protect our current theories. If those theories are incomplete, learning their limitations is progress. If nature has chosen a more complex solution than we anticipated, understanding that solution is triumph. Gravastars would be a gift, a chance to learn about quantum gravity and vacuum structure, and the physics of extreme conditions. They would be natural laboratories operating at energy scales we cannot reach with any particle accelerator. They would be windows into regimes our current theories cannot describe. They would be proof that the universe still has surprises waiting for us. The next decade will tell the story. Gravitational wave detectors will reach new sensitivities. X-ray observatories will map spectra with unprecedented resolution. The Event Horizon Telescope will image black hole shadows in exquisite detail. Stars orbiting the galactic center will complete new orbits under constant observation. Every year will bring new data testing whether gravastars exist. The evidence will accumulate or fail to accumulate. The signatures will emerge or remain absent. Within 10 to 15 years, we should know the answer, not from one dramatic observation, but from the weight of evidence across multiple wavelengths, multiple techniques, multiple objects. If gravastars are confirmed, the headlines will capture attention worldwide. Scientists discover objects 100 times stronger than black holes. Reality stranger than fiction. The universe's most extreme objects, not what we thought. These headlines will be accurate, but will miss the deeper significance. This will not just be about finding a new type of object. It will be about learning that quantum mechanics and gravity merge in ways we are only beginning to understand. That vacuum is richer and more complex than we imagined. That nature avoids the singularities and paradoxes our classical theories predict. That the universe at its most extreme is more bizarre, more beautiful, more intricate than we dared imagine. We have spent 50 years studying black holes. We have made them familiar through countless papers and lectures and documentaries. We think we understand them, but perhaps we have been studying shadows all along, approximations and simplifications, missing the deeper truth that lay just beneath. Perhaps the universe has been showing us gravastars for decades, and we have been calling them black holes because we did not know to look for the differences. Perhaps the most extreme objects in the cosmos, the ultimate products of gravitational collapse, the densest, most powerful, strangest entities permitted by physics, have been hidden in plain sight. Not hidden because they are rare or distant, but hidden because they look almost identical to what we expected to see. Almost identical, but not quite. And that difference, subtle as it is, changes everything. The universe is about to reveal its true extremes. We have found billions of galaxies. We have mapped the cosmos in detail, but we have not yet found its ultimate limits. Gravastars, if they exist, might finally show us how far nature can push the laws of physics, how strong gravity can become, how extreme the universe can be. We thought black holes were the answer. We might have been asking the wrong question. The universe is about to teach us what we should have been asking all along.